All right, have you ever run into a math problem where you know there's an answer, but the real puzzle is what kind of answer is it? Well, that's exactly what we're diving into today, the really curious case of homogeneous systems of linear equations. It's a mystery where the solution always seems to be zero, or is it?
So, first things first, what makes a system homogeneous? It's actually super simple. It just means that every single equation in the set is equal to zero. That's the whole deal. You can think of it like a perfectly balanced scale, where everything on one side adds up to exactly nothing on the other. That's the core idea.
And this is where they start to get really interesting. See, unlike a lot of other algebraic puzzles that might just have no solution at all, a homogeneous system is always consistent. That means you are guaranteed to find at least one answer every single time. No dead ends here. Okay, so if an answer is guaranteed, where's the mystery, right? Well, the question isn't if a solution exists, but what kind of solution we're going to find. Are we on a nice, straightforward path to a single, simple answer? Or are we about to stumble into a wild rabbit hole of infinite possibilities? That's what we're here to figure out. It turns out every homogeneous system leads down one of two paths. Path number one is what we call the trivial solution. It's simple, it's clean, it's where every single variable just equals zero. But path number two, the non-trivial solution, this is where things get interesting. This path means there isn't just one answer, but a whole infinite number of them. So the big question is, how do we know which path our system is on without getting completely lost? Well, luckily for us, we've got a couple of really powerful tools to act as our guides. Let's kick things off with a pretty clever shortcut. Our first guidepost is something called the determinant. You can think of it as this one single powerful number that we can pull right out of the coefficients of our variables. And this one number, it holds the key. It tells us exactly which path we're headed down. And here is the beautiful simplicity of the determinant rule. If that number is anything other than zero, could be 5, could be -20, doesn't matter, you are on the trivial path. The only solution is the zero solution. But if the determinant is exactly zero, boom, you've just unlocked the non-trivial path, the one with all the infinite solutions. All right, let's put this rule to the test, shall we? We've got a system here, 2x minus y equals 0, and x plus y equals 0. So are we looking at a trivial solution or a non-trivial one? Let's find out. Here's our game plan. It's a simple three-step process. First, we're going to build a matrix from the numbers in front of our variables. Second, we'll calculate its determinant. And finally, we'll see if that result is 0 or not. Okay, so our coefficient matrix is going to be a 2 by 2 with the numbers 2, -1 on the top row and 1, 1 on the bottom. To get the determinant, we just multiply the diagonals and subtract. So that's 2 times 1 minus -1 times 1, which gives us 2 plus 1. And the result is 3. So our determinant is 3. And since 3 is obviously not 0, our rule tells us we've got a unique trivial solution. And just like that, we know our path. The only possible answer here is that both x and y have to be 0. Mystery solved. For this one, anyway. Now, the determinant is a fantastic shortcut, especially for square matrices. But what's the deeper principle at work here? To really get that, we need to talk about a more fundamental concept, the rank of a matrix. This, my friends, is the ultimate test. It works for any system you can throw at it. So what exactly is rank? Well, imagine you have a list of instructions, but some of them are just repeats of earlier ones, maybe phrased a little differently. The rank tells you how many truly unique instructions you actually have. It's the thing that cuts through all the redundancy to show you what's really going on. The rule for rank is all about a simple comparison. We take the rank, which we'll call R, and we compare it to the number of variables, which we'll call n. If r equals n, it means you have just enough unique information for one single trivial solution. But if r is less than n, you don't have enough info to lock down a single answer, and that's when you get those infinite non-trivial solutions. Okay, time for a bigger challenge. This system has 3 equations and 3 unknowns. Now we could calculate the determinant, but it'd be kind of a pain. So let's use our new, more powerful tool, rank. Our mission is to simplify this matrix down and then just count how many non-zero rows are left. That number is our rank. So as we go through the steps to simplify this matrix, something really cool happens. That third row completely vanishes. It becomes all zeros.
And this is a huge clue. It's telling us that the third equation wasn't really giving us any new information at all. It was just a hidden combination of the first two. It was redundant.
So what are we left with? We have two non-zero independent rows. That means our rank is 2. Now we compare that to our number of unknowns. We had x, y, and z, so that's 3. And the result is crystal clear. 2 is less than 3.
And because our rank is less than our number of unknowns, we know for sure that this system is on the non-trivial path. It doesn't have just one single answer. It has an entire infinite family of solutions. We found our way again. You might be wondering, what do infinite solutions actually look like? Well, it means we have what's called a free variable. We can basically pick any value we want for one of the variables. Let's just call that value k. And then we can solve for the other variables in terms of k. And every single different number you pick for k gives you a brand new, perfectly valid solution.
Whew. Okay, so after that journey into the whole zero equation mystery, let's quickly recap the essential tools you now have in your toolkit to solve any homogeneous system you come across. So remember these key points. First, these systems always have a solution. Your job is to figure out if it's the one single trivial solution where everything is 0 or the infinite non-trivial solutions. For square systems, the determinant is your go-to shortcut. If it's not 0, the solution is trivial. And for any system, the ultimate test is rank. If the rank is less than the number of variables, you've hit the jackpot of infinite solutions. And that brings us to one last really crucial thought. That 0 solution, the trivial one, it often represents stability or, well, nothing happening. A bridge that isn't vibrating, an economy in perfect equilibrium, a circuit with no current. So in the real world, in fields like engineering or economics, what does it mean when you find a non-zero solution? It means something is happening. The system is dynamic. There's movement. There's energy, maybe even instability. And a lot of the time, finding that is the only thing that really matters. Something to think about.